Hello everyone, my name is Christian and this is the principal component analysis of PCA presentation. Our team members are Esau Maice, Amaury Castellanos, and Mónica Hernández. The following topics that we are gonna explain during this presentation are the definition of PCA, how to apply the PCA, what is the eigenvectors and eigenvalues and how to calculate, the covariance matrix, how find the PCA, and finally, an example. So let's start with the presentation.
How can we extract essential information and reduce the complexity of our data in a training model with complex datasets? Well, the answer is PCA. PCA is a statistic method that is used to reduce the dimensionality of a dataset. This technique helps us to simplify a dataset and choose the smaller number of predictors to predict a variable. So this will help us to understand in a better way our database. So how can we apply PCA? The first step is standardization. Standardization is a process used to transform data into a common scale format, making it easier to compare and analyze different datasets. It involves subtracting the mean, the average of the data, and dividing by the standard deviation. This results in a new set of data with a mean of 0.
I will continue talking how to apply PCA. Step 2 is the covariance matrix computation. The covariance matrix is a crucial concept in PCA, an important part, because it provides a measure of how much two random variables or features change together. And it also helps us to understand the relationship between different features and how they vary together. First step is understanding covariance. The covariance is between two variables is a measure of their joint variability. Positive covariance indicates that one of variables increase and the others tend to increase as well. And a negative covariance means that as one variable increase, the other tends to decrease. Second step is the of the covariance matrix is that we calculate the covariance matrix of the dataset. In this matrix is square uh, and symmetric. The element in
So, what are the eigenvectors and eigenvalues? The eigenvectors are special vectors associated with a square matrix, and they represent directions that remains unchanged when the matrix is applied to them, only scaling by a factor known as the eigenvalue. In other words, an eigenvector points in a direction that, after a transformation, it still points in the same direction, and sometimes with a different magnitude. Eigenvalues, on the other hand, are scalar values that indicate how much the eigenvectors are scaled during this transformation. So, to get the eigenvectors and eigenvalues, first we need to understand how to calculate the covariance matrix. So, here you can see that we have a database with 5 observations. Here is the x and the y and z. So first we need to calculate the mean for each dataset. So we need to calculate the mean for the humidity, mean for the temperature, and light. And here are some examples of how to do how to calculate the mean for each one. And then we need to calculate the covariance matrix. To calculate the covariance matrix, we need to use this equation. And yeah, here's an example of how to do this equation. Um, we need to do it uh, depending on the number of observations in our database. And yeah, that's what are eigenvectors and eigenvalues and the first step on how to calculate the covariance matrix.
Well, now I'm gonna explain the following steps to calculate our eigenvalues and eigenvectors. As Monica said, this is the final. Well, this is the formula that we need to follow to complete our covariance matrix. This is the formula, as Monica explained it before. So this is how does our covariance matrix looks like or must look like. In this case, for example, we have, let me choose a pen. Yeah. In this case, we have the covariance of between the humidity and humidity. We have the covariance of temperature and humidity. We have the covariance of light and humidity. And then we have the temperature section, and we have to calculate the covariance between each data set. The temperature with each data set. For example, temperature, the covariance between temperature and humidity, or humidity and temperature, and the covariance between temperature and temperature, the covariance between light and temperature. And finally, we have the covariance between the humidity and light, the temperature and light, and the light between light. Once we have this covariance matrix, let's calculate the eigenvalues and eigenvectors. In this case, we have the following formula. We need to calculate the determinant between this operation here, the matrix covariance minus lambda. This is what we are going to calculate, and the matrix of identity. So everyone knows how to calculate the following um, operation because everyone knows linear algebra. So assuming that our covariance matrix is the following results, we need to calculate with the formula, and then the results are the next: lambda 1, lambda 2, and lambda 3. These are lambda values, and this is the eigenvalues. Now we have to calculate the eigenvectors. And how are we gonna calculate the eigenvectors? We're gonna calculate with the following formula that is a bit the same pattern. So we need again our covariance matrix. We need to our covariance matrix we need lambda that we already calculated, and we need again the identity matrix, and all of this procedure multiplied by the eigenvector. And again, it's just a simple equation that we need to calculate the eigenvector, and yeah, that's it. For lambda 1, that we already know that lambda 1 is this value, we need to calculate with the following formula to calculate and have our eigenvector be 1. This is the matrix of P1. Then we have lambda 2. The lambda 2 is the following value, this value. And we have the result of B2, that is our eigenvector 2. And the lambda 3, this is the result for lambda 3. And what is next? The next step is to order each eigenvector and each eigenvalue. In this case, we already know what is and is completely clear that the eigenvalue lambda 1 is the highest and lambda 3 is the lowest. So our principal eigenvalue is lambda 1. So, and the next step is select what PCA are we going to use. Could be 2, could be 1, could be 3, depending. But in this case, we have just 3, and we're gonna choose just 2 PCAs. Okay. And The last step is the data projection. So to project the data, it is necessary to multiply by the observation by the eigenvalue that we selected before. In this case, we have the projection 1, the x1 projection, and the x2 projection. For example, in this case, we're gonna choose the observation 1. Observation 1 have 60, 25, and 500. So these values we're gonna put here in this matrix, and we're gonna multiply by b1, our eigenvector. For the x2 projection, we're gonna choose the next observation, in this case 2, with the following data: 55, 22, and 500. All of these data multiply by b2, that it was the eigenvector that we selected, because we select two eigenvectors, lambda1, lambda1 and lambda2. And lambda1, we already know that its eigenvector is b1, and the eigenvalue b lambda2, we already know that its eigenvector is b2. This is why we are multiplying each observation for the PCI that we already select. And yeah, that's it. And this is all for my part. And this is the end. Oh, and now it's time for explain more about the one example that is going to be presented by my partner, Amaury.
Let's imagine that we have a dataset with 1,000 observations and 5 parameters. We'll need to calculate the mean of each column and its standard deviation. We're going to use it to normalize our data. That means adjusting the values in each column so that we have a common scale and distribution. This will make it easier for us to compare and analyze the data. Once we have this, we calculate the covariance matrix. But before that, we need to center our data using this equation. Once our data is centered, we can obtain the covariance matrix and find our agent vectors and agent values. Then we choose our principal components. And we can graph our new set by multiplying the agent vectors times our observations and plotting it on the graph.